because of that kind of nature, it's liable to collision. So some other signals may be coming on the way and the two signals will collide. Okay? So we want to see how to detect collision, okay, and how to kind of recover from collision. Okay? That's what we'll see. So it's called carrier sense. Like I said, it sends for the signal and multiple axes. So every machine has equal access to the channel. So that's why it's called multiple axes. Okay? So they can access anytime they want. And if they see the channel to be free at the point where they're located, they go ahead and insert their signal on the channel. Now, so let's first look at this collision detection issue. How to detect the collision. So let me take up this figure here. Let's say we refer to two machines A and B. B is like something at the extreme. So let me just relabel them as A and B, like this. So A wants to send, A is one extreme and B is at the other extreme. So this kind of generalizes this. So A of course senses the channel locally, it sees nothing, so it inserts its own signal. And the signal propagates all the way to B. And just before the signal reaches B, B wants to send some data. And B senses the channel and the channel is observed to be free at that point. B doesn't see the signal yet. So B inserts its own signal. And the two signals collide and we get a jam signal. Okay? So look at this as a jam signal, it's like a different color. So the jam signal again goes to the entire bus or a channel. Okay, so that's what happens.
So it goes to where now?
It goes to the entire bus or channel. So whatever you insert will go to the entire channel. Okay. So what we want to do is we want A, the sender, to be able to figure out that its signal has collided with something else. So of course then what will happen? A has to retransmit its data, right? It has to send some data to B and that signal has collided. So A has to retransmit. So the first issue is how A detects the collision. Okay. So as I said, A will sense for the channel, it sees nothing and inserts its own signal, right? So for A to be able to detect the jam signal which is coming back, A has to keep listening to the channel until that time it can hear or see the jam signal, right? And not only that, if A has to sense it as a jam signal, it has to also keep inserting its own data signal. If A was just silently listening, okay, and some signal is coming, it could be the data signal of some other machine. Okay, so for A to decide that there was a collision of its signal, A has to keep inserting, or the sender has to keep inserting its own signal. So only when it keeps inserting its own signal, it can figure out that there's another signal on the channel which is coming because its signal got collided somewhere and the jam signal is coming back in the opposite direction. So which means the sender has to keep inserting its own data bits or the data signal on the channel until it can listen to a jam signal. Okay? So which means you cannot just insert a bit and expect that bit to propagate all the way to the receiver, and if that bit happens to collide with it, then you cannot really detect the collision, because if you just silently listen to the channel, you may not figure it out as a jam signal, it may be some other signal on the channel. Okay? So that means you have to keep transmitting at least for some time. And what is that time? Okay? Can anyone tell what will be the time that you have to at least keep transmitting before we can sense or detect a collision?
The bow.
What's that? And look at this as two extremes, right? So we are looking at a channel this side, not quite here. So you're looking at a channel of say some length. So we're looking at two extreme machines. So that's why I picked extreme machines. So the signal inserted by A travels to the extreme, the other end, and then the jam signal comes back, right? So which means you're looking at a channel of say certain length, and looked at two delays before. We looked at, I think, RS-232 standard. What are the two delays we looked at?
Transmission delay,
Propagation delay.
propagation delay,
And which delay applies here for the length? Propagation delay, right? So you want to propagate, the signal propagates for one length and then the jump signal propagates for another length. Okay? So we want to keep transmitting until delay, the time is twice the propagation delay. One propagation delay for the data signal and the other propagation delay for the jump signals. And what we have to do until then, we have to keep inserting our data bits, right? So we have to keep inserting the data bits until the jump signal comes back, which is twice the propagation delay. And what is the delay that you represent to keep inserting the data? Any bits? What's the other delay?
transmission.
Transmission delay. It captures the insertion time, how long it takes to insert the bits. So which means, let me use a different color, which means the transmission delay has to be at least twice the propagation delay. So that's what it is, right? So you have to keep inserting the data bits until at least twice the propagation delay, until the data, the jump signal comes back. Okay? So this is the fundamental thing that you have to remember. So once you remember this, all these equations could be derived. Now apply the, I don't know why it's like this. Yes, right here. So apply the definitions of the two delays. And before that, let me remove that equality sign, the greater than sign. So if I remove the greater than sign, I can call it as the minimum transmission delay. So the minimum transmission delay is twice the propagation delay, because it has to be greater than or equal to, right? So when I remove the greater than sign, we can say it is the minimum transmission delay. The transmission delay has to be at least twice the propagation delay. We can say the minimum transmission delay is 2 times the propagation delay. So now apply the definitions. So the minimum will stick with throughout this. So the transmission delay is the packet size. We can call the packet here as actually the frame. At the link level, we call the packet as a frame. Okay? So it's the frame size divided by the channel bandwidth. And it is 2 times the channel length divided by the speed of the signal on the channel. So I'm just applying the definition of the two delays. So now if you just do a cross multiplication, I can say the minimum transmission delay, the minimum frame size is 2 times the channel bandwidth times the channel length divided by the speed of the signal on the channel. Okay? So that is the equation.